Let's start a series on atomic, molecular, and nuclear physics. I'm going to call this atomic physics in short, right? So to study the subject of atomic physics, we will need a lot of tools from quantum mechanics. And so to begin this first lecture in the series, I will start off with the revision of angular momentum. So let's just get into it and start with the classical orbital angular momentum of a particle. So that is defined as L vector is equal to R cross P. Over here, R and P are the position and momentum vectors of the particle, where this P is your linear momentum of the particle, right? So in the position basis, you can write the components of angular momentum as your operator angular momentum, that is Lx. So this hat stands for the fact that it's an operator now that we're talking about. That means we're in the quantum mechanics world, right? So that is given as y pz minus z py, where these y, z, they're just the coordinates, right? Positions. And we have this thing is equal to, if I convert my momentum into the operator form of the momentum, right? So what do I have? I will I should write these operators, right? That these momentum are operators, and I'll have negative iota h bar, and that I can factor it out because it's just a constant. And I'll have y partial derivative with respect to z minus z times partial derivative with respect to y. Corresponding to this pz, I have this partial derivative with respect to z and this negative iota h bar. Or let me just write this thing down over here, that if, for example, I'm talking about p in x, right? And it's an operator, the operator is represented as a negative iota h bar partial derivative with respect to x, and likewise for y and z. Of course, I'm not going to go in the depth of all of these things because this is just the revision of angular momentum. And so if you want to go in a much more depth, you should watch some other lecture on, and that is completely dedicated to angular momentum. But I will try to cover as much as I can, right? Okay, so likewise I can have this Ly component would be z px minus x pz, right? And this thing would be equal to negative iota h bar z partial derivative with respect to x minus x partial derivative with respect to z, following the same procedure that we did over here, right? And then we have Lz operator as x py, and even these y, z, these are operators, right? So let me just draw this hat on these things, right? Because the momentum operator is this thing and the position operator is just itself, right? Okay, so yeah, minus y p x, and this thing would be equal to negative iota h bar x partial derivative with respect to y minus y partial derivative with respect to x, right? And these now, the important thing over here is that the components of your angular momentum, they cannot be measured simultaneously. Mathematically, that is to say that the commutator of, for example, Lx and Ly is non-zero. So it has some value which turns out to be iota h bar Lz, right? And likewise we have for Ly and Lz, commutator is iota h bar Lx, and we have for Lz and Lx, it is iota h bar Ly, right? And so what this means is that it is impossible to find a representation that diagonalizes more than one of these components. That is, that the components of angular momentum cannot be simultaneously measured, right? But there is something that we can do, and that is if we introduce the square of angular momentum, that is L squared, right, which is defined as simply Lx squared plus Ly squared plus Lz squared, right? Then it turns out that if I take this commutator, that is L square Lx, and if that is equal to, if I were to take the commutator L square Ly, which is equal to the commutator of L squared Lz, and all of these commutators vanish, so it's 0. So what this means is, with L squared, it is possible to construct simultaneous eigenstates of L squared and one component of your angular momentum, so that L squared and its component can be simultaneously defined precisely. Now, it is rather more convenient to express this Lz and L squared in spherical polars, right? Which are your r, theta, and phi. And these spherical polars are actually related to your Cartesians x, y, and z. And these are for this position vector r, right? So if I were to draw this thing, right, let me just quickly draw a rough sketch, which I am not good at, but yeah. So if I were to have some position vector, right, for a point P over here, and this position vector is r, right, which is just the magnitude of the vector r, right? And it is important, of course, to note that this is my y-axis, this is my x-axis, and this is my z-axis, right? And the angle that this position vector makes with z-axis, let's call that theta. And the projection of this in your y-x plane or xy plane of this position vector is this vector that I drew over here in this dotted line, right? Or let's just draw a proper line, right? So this is the projection of this point P, position vector, and the angle that this projection vector makes with x-axis, we'll call that phi. Now, looking at this vector diagram, we can write down this relation between polar coordinates and Cartesian coordinates as x is equal to r sine of theta times cosine of phi, right? And we have y coordinate is then simply r times sine of theta times sine of phi. And my z coordinate finally is simply r cosine theta, right? And the limits on these r, theta and phi are defined as this. When I write this thing, right, I just mean width. So with r going from 0 to infinity, right? So it could have a position vector. It is not limited, right, to have this much length. And theta goes from 0 to pi, and phi goes from 0 to 2 pi, right? And I think I should mention, but if you have been watching my videos, you probably know this, that my sines and cosines, I use this different symbol. It just helps me because I'm lazy, and so I don't have to write all that thing over and over again. So this theta inside the sigma is my sine of theta, and this theta inside this gamma is my cosine of theta. And we will have to use cotangent in this lecture as well. And so I write cotangent with C and this tau, symbol tau, right? Like this. This is C and that's tau. And inside this tau, if I have theta, that's my cotangent of theta, right? It's a very weird and funny notation that I use, but it's just that because I'm lazy, and so I'm mentioning this. It's not so hard to remember as well, right? Easy for me to say, but you get the point. So, well, let's move on and let's now write down the Cartesian components of L in spherical polars. So let's write them down. We'll have Lx be equal to iota h bar sine of theta times partial derivative with respect to theta plus cotangent theta times cosine of phi times partial derivative with respect to phi, right? So that's your Lx component in your spherical polar coordinates. Then we have Ly, right? And Ly is equal to iota h bar times minus cosine of phi partial derivative with respect to theta, right? Plus cotangent of theta times sine of phi times partial derivative with respect to phi. And finally we have Lz component, which is very easy. That's just negative iota h bar times partial derivative with respect to phi, right? Now from this set of equations we can easily obtain what is called the ladder operator, right? And the ladder operator is used to well, add to a state or remove from that state. So let me write this thing down. We have a ladder operator L plus, right? And this operator, what it does is it will increase the angular momentum by 1 unit, right? And it is defined in terms of Lx and Ly as such, right? So it's Lx plus iota Ly. Now we could expand this, right? And let's go and expand this using this two set of equations, right? That is for Lx and Ly. So if I do that, what do I get? I get my L plus operator as iota h bar sine of theta times partial derivative with respect to theta plus iota h bar cotangent of theta times cosine of cosine of phi times partial derivative with respect to phi. And then I have plus iota, right, which is this thing, right, this one. And now I'll write the Ly component from this equation, right? So what's that? That's iota h bar minus, or let's just put this minus sign over here, right, minus iota h bar, and then I have cosine of phi partial derivative with respect to theta plus cotangent of theta sine of phi partial derivative with respect to phi, correct? So now we could just put this thing in, as in multiply this I, and iota times iota is -1, and we have this -1 over here. So what happens is it becomes positive, right? So let's just do this thing, right? So that's what you have now. And now with this, in fact, what I missed over here was when I was writing this, right, this iota h bar also had to be multiplied with this thing when I open and write it. So I should have plus iota h bar over here. But then when I distributed this, when I had an iota in here outside over there, when I distribute it in, right, I had this previously. Well, let me just write this whole thing again, right? So now we have this equation, right? I'll multiply this iota with iota, and what happens is I get plus 1 over here, right? So it becomes positive. And when this iota gets multiplied with this, it becomes negative. So sometimes me being lazy is not so good, right? So I'll just add this negative sign, right? So that's it. And we'll of course have h bar over here. Now you could next thing you could do is just collect the like terms together, right? And your final expression for your L plus, it becomes exponential iota phi, right? Because you get this exponential form of sines and cosines, and that's what you get. So you have this thing plus iota times cotangent of theta. In brackets now we have cosine of phi plus iota times sine of phi and times partial derivative with respect to phi, and all of this times h bar, right? And so therefore we can say that L plus is represented with h bar exponential iota phi times partial derivative with respect to theta plus iota cotangent of theta times partial derivative with respect to phi. Right. Now this is your L plus, right? So you could say it's your raising operator. It raises the angular momentum. And you could, from this relation, that L minus is simply Lx minus iota Ly, you could compute yourself the value of L minus now, just as we did for L plus, right? And what you get is h bar exponential and negative iota phi times iota cotangent theta partial derivative with respect to phi minus partial derivative with respect to theta. And that's your L minus operator, right? And you could call this your lowering operator, as it lowers the angular momentum state. And now with this, then we can also write down L squared operator in terms of these spherical polars, right? Lx, Ly, and Lz squared. So once you compute that, you just get negative h bar squared times 1 over sine of theta, partial derivative with respect to theta, times sine of theta, partial derivative with respect to theta, plus 1 over sine squared of theta times partial derivative with respect to phi. In fact, partial square, right? Okay, and this is then your L squared operator in spherical polars, right? And the eigenfunctions, we'll call the eigenfunctions of Lz as, let me write this down over here, eigenfunctions of Lz, will denote them with this capital phi as a function of phi, right? And these eigenfunctions, they satisfy the eigenvalue equation for Lz, which is Lz acting on these eigenfunctions, and they give you m h bar phi of phi, right? Now quickly recall that we just said Lz from here, this thing, right? This is our Lz, which is negative iota h bar partial derivative with respect to phi. So Lz is negative iota h bar partial derivative with respect to phi. Let's substitute this thing in this. So what do you get? You get negative iota h bar partial derivative with respect to phi of this thing, right? Of phi is equal to this whole thing, which is m h bar phi of phi. Correct. So the solution to this differential equation over here is simply this thing, right? Phi is equal to some constant a times exponential iota m phi. And you could check that by substituting this thing in your equation, differential equation, and it would satisfy it, right? And if you use the orthogonality or normalization condition, you figure out that a is simply 1 over 2 pi, right? And so therefore then I can finally write down my eigenfunctions of Lz as 1 over 2 pi 1 over under root 2 pi times exponential iota m phi, right? Now since the functions, these ones, right, must be single valued, we have to impose, or we have this condition that phi of phi, sorry, I'm so sorry, it's phi m of phi m, what am I saying, of 2 pi. So the value at 2 pi should be the same as the value of this function at 0 degrees or radians, right? And that is simply because this this thing, there should be an m. This m simply represents that it's just a function with this m quantum number, which is called the magnetic quantum number, right? And in fact, this magnetic quantum number is restricted to positive or negative integers, or it could be 0. So let me just write that down. In fact, the values that m is allowed are plus minus 1, 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4. Well, somewhere I have to stop, so let's just do this, right? And also note that this eigenfunction phi of phi m of phi is orthonormal. What does that mean, right? So it's instead of drawing these two dots, is orthonormal. Mathematically, that is just to say that if I were to integrate these functions, right, as phi star of phi m m prime, right? So this, it is just some other phi, it is in the dual space, right? And that's why we are taking this conjugate, and if we multiply it with phi of phi, and we integrate it with respect to phi from 0 to 2 pi, it should give you delta m m prime. What that means is, well, if m and m prime are same, it would give you 1, and if they are different, it would vanish, right? It would give you nothing, right? So, well, in the bracket notation, that is simply this thing, right? So the inner product, which is delta m m prime, right? Now the simultaneous eigenfunctions of L squared and Lz, they are called spherical harmonics, right? So the let me say this again, the simultaneous eigenfunctions of L squared and Lz, right, they are called spherical harmonics. And spherical harmonics then are represented by y Lm theta phi, right? So in fact, these spherical harmonics also satisfy some eigenvalue equations, and let me just write those down. So L squared acting on these spherical harmonics, theta and phi, is equal to h bar squared L times L plus 1, and you get your function back as it is, like this, and you have Lz acting on y Lm. It gives you m h bar and your function back as it was. Now over here, this L, it is known as the orbital angular momentum quantum number, right? Okay, now we need to solve these equations, right? And so to do that, we will set this thing that y Lm theta and phi, they can be written as some capital theta function, right, as a function of theta, right? Yeah, and multiplied by, in fact, this theta would contain L and M, and multiplied by this phi m of phi. Now we already know what this is, right? We just figured it out over here, right? We know what that is. The task now is to figure out what this function would be. So for that, we you see, we have L and M both in this, and this was with just M. So which of these two equations should I solve? Well, I have L in this, and in this one I don't have any L, right? So it just from there I can just figure it out that well, I have to solve this one to figure out these functions, right? So let's go ahead and well, do that. So we'll have L squared. Now instead of saying it to be acting on this thing, well, it is acting on this thing. Let's write it down in terms of its this thing, capital theta Lm theta times phi, capital phi m as a function of phi, which is equal to h bar squared L into L plus 1 times the function back, which is this now. So it's capital theta Lm theta capital phi m of phi. Right. Now the next step would simply be to write down this L squared in spherical polars. So what is that? That is negative h bar squared 1 over sine theta partial theta, and that is partial derivative with respect to theta of sine theta partial derivative with respect to theta plus 1 over sine squared theta partial derivative squared with respect to phi, right? And we have now these functions, so let's just write these down. Theta Lm of theta, phi m of phi, right, which is equal to this thing over here, right? So h bar squared L into L plus 1, and I don't think I'll have space, but this part, right, this part, it comes over here, right? Okay, so now, well, let's quickly note that this thing, partial derivative with respect to phi of capital phi m, right, and know that we have computed this thing, so we just have to take let me just go back over here. We have to take the derivative of this thing with respect to phi. So let's, well, quickly do that, and that's simply iota m over under the root 2 pi times e to the power iota m phi, right? And if you were to take the double derivative with respect to phi, right, of this thing, this, you would simply get negative m squared and the function as it was, sorry, like this, right? And well, the need to take these derivatives were because we have this thing, right, and it is acting on this thing as well. So from here now we have this equation as we can rewrite it down as negative 1 over sine theta partial derivative with respect to theta, sine theta partial derivative with respect to theta plus m squared over sine squared theta, right? Again, I'm just writing this equation with putting the value of this derivative, right, in here. So yeah, then I have this function that I still have to figure out, theta of theta, it is Lm, right, and this is equal to L into L plus 1 times this capital theta of theta Lm, right? It is important to note that I have simply cancelled out these, and this one that would have been over here, I would have cancelled it out after I took this derivative and I got the function back, right? That's why I was able to cancel this thing out, right? After applying the derivative operator. That is important over here to note, right? Otherwise, I could have simply not cancelled it out because there was an operator acting on it, right? So let's just get rid of these lines, right? And now, well, next step from this equation is to multiply it with sine squared theta, right? And what we are doing is we are trying to solve this equation with the if you know from mathematical methods, the separation of variables, right? And we'll see the solutions to this equation are well, we'll see, right? I would not like to spoil it for you. It would be like a spoiler. So from here now, like I said, we will multiply it with sine squared theta on both sides of this equation. And on doing so, we get negative sine squared theta over sine theta partial derivative with respect to theta times sine theta partial derivative with respect to theta plus m squared, right? This sine squared that was over here, it goes away. So yeah, and we have this lm theta equal to, over here we multiplied with sine squared theta, so we'll have 1 sine squared theta and L into L plus 1, and this lm theta, right? So well, there is a lot of mathematical calculation going on, but that's what you opted for, right? So the next step over here is just to simplify this, and let me just write down the final result. We rearrange the terms, right? And what we get is sine theta times, now the dependence on phi is, well, it's completely gone, right? So we just have the dependence on theta. So instead of using instead of using partial derivative, we'll just use the total derivative. So that's just d theta, that means derivative with respect to theta. And we have sine theta derivative with respect to theta, and our function, right? I don't have to keep writing that, it's a function of theta, plus L into L plus 1 times sine squared theta minus m squared theta lm as a function of theta is equal to 0. Now this is the equation that we need to have the solutions for, and it turns out that the only physically acceptable solutions of this equation that remain finite over our range of theta that was from 0 to pi, they exist if and only if we have L as 0, 1, 2, 3, 4 and up to so on, and the values for m being negative L and negative L plus 1, negative L plus 2 up to L, right? So yeah, the only physically acceptable solutions of this equation exist with these, when this is true. So the solution to this equation, it is expressed in terms of the associated Legendre functions, right? And let me write it down. So the solutions to above differential equation are associated Legendre functions, or the Legendre polynomials, well, you could, and you write them down as PML of theta. So then that means that the solutions to this equation are this capital theta Lm as a function of theta is equal to, so these functions are some constant a times PML of theta. Well, in fact, not theta, we have, even over here we don't have theta, it is cosine of theta. So cosine of theta, right? And over here this PML is the associated Legendre function. And let me write it down what it is, right? So it is defined by, let me write it down as, sorry, you would have as some x, right, as some function of x variable. They are equal to 1 minus x squared time in the power we have absolute value of m over 2 times derivative with respect to x with the power of absolute value of m, and p L times x, right? Now in this definition, what is PL? Well, PL of x is the nth Legendre polynomial, and we can define PL of x as 1 over 2 to the power L times L factorial times derivative with respect to x to the power L times x squared minus 1 to the power L. And that's how you define the nth Legendre polynomial. And so using these expressions, you can calculate these PL of x for different values of L. So for example, if I were to compute P0 of x, I have to substitute in this L, I have to put 0, right? And so if I do that, what I get is plus 1. Likewise, I could compute for P1 of x. All I have to do is substitute this value in L, right? Which is 1. And so once I do that, what I get is x. And likewise, you could calculate more. Let me just write one more down. P2 of x, where L is 2, you get 1/2 times 3x squared minus 1. And you get so on, right? Now, there is orthogonality relations for this nth Legendre function or polynomial, and it reads as this integral from -1 to +1 PL of x times PL prime of x dx, which is equal to 2 times 2 over 2L plus 1 times delta L prime. And so, well, the first few Legendre functions, they are, let me write them down, right, explicitly. So P11, right, with m and L both equal to 1, we have, well, this would be a function of x, which is 1 minus x squared, 1 by 2. Then you could have P where L is 2 and m is 1 of x, which would be equal to 3 times x times 1 minus x squared 1/2, right? And you could have so on, right? You could write many more of them using this orthogonality relation, right? And these set of two equations, right? Now these functions that we just figured out, right, the ones that we were just calculating, these ones, they are normalized such that this integral 0 to pi, right, that was the limit on theta, this conjugate of this thing, so L prime M prime theta times this function Lm theta, and so we would have over here a sine of theta d theta, right, and that is your differential in terms of spherical coordinates. It's delta L times L prime, right? And so with this, then we can write down theta Lm of theta as minus 1 raised to power m times square root of 2 L plus 1 times L minus m factorial over 2 times L plus m factorial, all of this multiplied by PLM as a function of cosine of theta, right? And with m is greater than equal to 0. So this is the expression that you have for your this function, right, theta Lm. Now from this, the explicit form of spherical harmonics, right, the explicit form of spherical harmonics, they are given by y ml theta phi, right, which is equal to minus 1 raised to power m square root of 2L plus 1 times L minus m factorial over 4 pi times L plus m factorial, right, times P ml as a function of cosine of theta multiplied by exponential iota m phi, where note that this thing was your solution to the LZ eigenfunctions, right, where you had that constant 1 over under root 2 pi as well with exponential iota m phi, which this constant was dissolved into this thing, right? And that's why we did not, instead of having 2 over here, we had this 4 pi. So under root 2 times under root 2, and we had this factor of under root pi as well. So we substituted in for that. So yeah, let me get rid of this thing that I just wrote. Yeah. So with this, another important property of the spherical harmonics is that yml of theta and phi actually y, it's not this thing. Let me rewrite this whole thing down. Y, L and minus m, right, of theta and phi is equal to the minus 1 raised to power m and the conjugate of ylm of theta and phi. So this is just one of the property, and this is how your spherical harmonics are written, right? Again, with m for these is greater than equal to 0. Right, now well, before I just end this video, let me just also say that these spherical harmonics also satisfy the orthonormality relation, which is mathematically written as the integral of y L prime M prime, right? Y conjugate theta and phi times y L M theta and phi integrated with this d omega, and I'll just tell you what this d omega is equal to 0 to 2 pi, and d phi was going from 0 to 2 pi, right? And this integral for d theta, and this differential for in spherical polars is d theta times sine of theta, right? And theta, remember the limits were from 0 to pi, times y star L prime M prime of theta and phi times y Lm theta and phi, right? And all of this integral is simply equal to the delta M prime. And we have also delta L and L prime, right? So it's equal to this thing. Now this d omega, it is also called as the solid angle. So d omega is equal to sine of theta times d theta d phi, right? And so with this, I would like to end this lecture over here. It has already gotten really long. In the next part of the review on angular momentum, I will specifically talk about the matrix representations of angular momentum. And well, this was just the revision of angular momentum, but I hope I was able to cover a lot of things in here, right? And you were able to understand it as well.